And is it, let's see if the camera works. Oh, that looks okay. And share the screen. All right, so we'll get started in just a second for everyone. Okay, Zoom is there. Projector is not cooperating. Nope, nope, it just takes time. Cool. Let's get that out of the way. Let's pop up Zoom chat. All right, so those on Zoom, if you can't hear or see anything, just let me know, but I think we're all good. So today we're going to talk about programming paradigms. This is going to be a little bit of a shorter lecture, so if there's time left over, I'll take generic questions. We'll have, in the same way that there are a couple short answer questions at the beginning of the quest, you can probably expect that there'll probably be about one, but no more than 2 short answer questions on today's lecture, but they'll be pretty high level. So just sort of a note about where we are in the class. So Monday was, and we'll show some Snap code today, but Monday was sort of the last Snap lecture that was in Snap for a little while. After the midterm, so again, next Monday's lecture will be open-ended Q&A. After the midterm, we'll start with transitioning from Snap to Python. And so that lecture will be about writing code in Python, comparing Snap to Python, and so on. We'll come back to Snap later in the semester a little bit. But as you're thinking about this, what I'd say is, like, for the next week, focus on making sure you know, everything I've been doing in Snap, you understand that. The midterm will be, of course, 100% in Snap. But starting with next Wednesday, and then for the last few weeks of the semester, you'll get to have the choice of whether or not you want to program in Snap or Python. And I can promise you that having had the experience of you know, seeing multiple people go through final projects, we'll talk about sort of, you know, the specs of that later. But, you know, Python itself, even though it's quite similar to Snap, the hope and general feeling for most students in the past, right, is that Snap is great preparation for Python, but Snap gives you a lot of tools that you don't get for free in Python. And so as you're just thinking about the types of things that we can do in programming languages and what you can build, don't immediately feel like you want to just jump to Python because it's cooler or because it's harder. There are so many cool things that you can do in Snap, which of course you can do them in Python as well, but by having that environment and built in. So today what we're going to talk about then is actually is programming paradigms. But before we get to that, just more updates for the midterm. So we're going to send out an email either tomorrow or Friday with the exact you know, reminding everyone of locations, but we do now finally, it takes a while around campus to get everything confirmed. So we have 2 rooms for the midterm, 2040 and 2060 Valley. They are, if you go sort of where 2050 is the big lecture hall, one is on the left, one is on the right, at least from, you know, that entrance by sort of FSM Cafe. 2040 and 2060, they're each smaller rooms, so we're going to split people up. Even student IDs, or let me just say what's on the slides. Odd student IDs will go to 2040, even student IDs will go to 2060, but again, we'll write that out on the email. If you want to take the exam remotely, you can fill out the form, you'll take it on Gradescope. If you took the quest remotely, sort of same deal as that. Again, same exam, remote stuff is proctored. One thing we'll ask is that though there's not a campus requirement, please do wear your masks for the midterm. And I do appreciate that most people are wearing masks in class. In general, I think like everyone has been awesome about this on campus. I am like a dozen feet away from the closest person. So hopefully like we're figuring out boundaries and what works as things go along. But yeah, otherwise tomorrow in the evening, there'll be a midterm review session led by the TAs. That cut out. That will be all over Zoom. So ask questions, during the year, and then Monday during lecture will be sort of any last second things to go over. And then just a reminder, we do have the collaborative policy in CS10. So any later exam, if you improve as a percentage, will raise the score on your previous exam. So what that means is if you got let's say a 70% on the quest and you get an 80% on the midterm, your quest score becomes an 80%. Similarly, if you get like 80% on the final, then your midterm and quest scores would raise to an 80% if they're lower. And of course, if your previous exam scores are higher as a percentage, those don't drop. And your final can cover the midterm or the quest, or one or the other, or whatever it needs to. Again, exams meant to be a progress check. Hopefully don't stress about them too much. So today we're going to talk about programming paradigms. And this is one of those things where it's a little bit of an esoteric idea, but I think it's super useful in thinking about why we actually talk about the constructs that we have. Why do we like beat you over the head with map keep and combine to an extent? Why do we like, impose topics like recursion? Because when we talk about writing code, what we can talk about is the ways in which we write code to help us understand how to write it. So a paradigm in general is just what we can say is a typical example or pattern of something. So it's a model. So what we're really talking about here are different styles of how we write code, not necessarily at an individual line of code level, although there are examples of that. But when we think about the programming language, the environment, multiple functions, a whole file, and so on. And so a programming paradigm in particular is what we can say is a general approach, orientation, or philosophy of programming that can be used when implementing a program. And what that means is that when we look at the slide like this, we have three different sets of blocks in Snap that all actually do the same kind of thing. So we have a square block, which in Snap, we don't explicitly ask you to memorize these things, but these three little dots right here indicate that this X value should be a list. And by the for each item, where we say for each item of X, that indicates that this should be a list. So we have a square block that takes in a list as an argument. We have a map times over a list of numbers. And of course, we have the multiplication block, which accepts a list as a set of arguments as well. And each of these blocks takes in those sets of numbers, returns the square of those values. And each of these three has a distinctly different style. Which one you prefer, which one is your favorite, which one makes the most sense. Those are all things which are valid sort of personal views that, well, professors and people online have debated for as long as there are programming languages. So saying that one is necessarily better than the other is not the point, but the point here is to recognize that there are different styles of these types of things. So why do we talk about these styles? Well, the hope is that understanding and recognizing a paradigm will help you think about what are the other types of things that this code is doing? When I see a list of data, how do I understand how that list might be used? And by recognizing a pattern, that helps you make sense of their code. The other part of this is that some of these patterns, while all of them are equally good in the sense that they can solve all the problems, is that they do different strengths and weaknesses. And so one of our goals would be to sort of pick the right tool for the job, so to speak. And that in this class, we're not necessarily going to ask you to always use a particular paradigm. We're going to say, like, if you get something working, that's the goal in CS10, but you might find as you work on a lab or a project, that using some of the built-in tools in Snap in one way or another aid you in that goal. And the other part is most of the programs that we write today, most of the languages that you'll be using, this includes Snap, this includes Python if you take CS10 or CS88, or any of the data science courses, Java and CS61B. All of these languages are in many ways multi-paradigm languages in that they support more than one style, and they borrow the best and sometimes the worst of all of the styles that exist. So before we continue, just a word of warning that there is sort of no universally agreed upon list of of programming paradigms. There are generally 4 that people mention, and there's 4 that Berkeley typically teaches, and you'll notice that this list has 5. So I'll highlight that difference in a second. It is just worth noting as a fun example, because it's in the slides, there's a Wikipedia page on programming languages. I will say the computer science articles on Wikipedia, generally pretty good. Each Wikipedia page comes with a talk page, which is how the sort of editors and community contributors to Wikipedia think about a particular problem. So you can kind of scroll through here and see the things that maybe these are paradigms, maybe they're not. What do other people think? Unlike the rest of the internet, the talk pages of Wikipedia are on average pretty civil. Some of them get a little uncivil, which is entertaining. So we have 5 paradigms that we're going to talk about: imperative, functional, array-based, object-oriented, and declarative. And array-based is the one that, again, this is not exhaustive, but array-based is the one that we don't normally talk about. But with some changes in Snap, there's a lot of interesting things to explore about why this is a useful paradigm. So we've kind of added to the list. But typically you'll hear imperative, functional, object-oriented, and declarative. Certainly, functional and object-oriented are things which have really strong histories of other programming languages existing. So you may have heard that Java is an object-oriented programming language, a statement which is probably meaningless to most people, but we'll sort of talk about what objects are in a second. Objects in Snap do exist. They're a little bit weird to demo. So here are the examples for the previous slide. Is a functional programming paradigm typically involves taking a function and just using that result and passing it to another function. So when we talk about the distinction of pure functions, what we're really saying is we want to compute a value, pass that value along, and that we're thinking about how we take some data into a function, use that result. We're not typically assigning variables. We're not typically explicitly using loops, but we're thinking about applying a function to a list, passing data in, getting the result back, sort of what we typically think of as just really computational tasks. Array-based programming is, in many ways, a distinct type of functional programming or a separate category, but it's really thinking about how do we explicitly design a programming language and an environment that works really well on lists of data. So array is just another computer science term for list. People will have arguments about what's a list and what's an array. Those are not worth having. But if you see array-based, just think list-based. In Snap, we just call them lists. And you'll notice, though, in this case, like 1, 2, 3 times 1, 2, 3, it does the same effect, but it is perhaps a completely different and distinct way of thinking about how we might write programs. And so that's why it gets called out as a separate category. In Snap, actually, why don't I just pull this up because I think it's an interesting example. In Snap, there is a libraries sort of browser. So Snap, while it has about 170 or so built-in blocks, has a bunch of libraries that come with Snap. Some of these are really simple, like, where is it? We have it's called Pixels, which bothers me because it's not what it does. We have a Pixels library, which allows you to take a photo from your webcam and sort of report the image back. That should just be called the camera library. But we also have things like this library called APL primitives. And APL happens to be this language that originated in the 60s that's all about doing data computation on lists of data. So thinking about things like linear algebra, where you have matrices and arrays. In the 60s is sort of when the term data science started to originate. There are a whole bunch of functions, which I'll be honest, even I do not understand all of these because they are built for a particular style of programming that I don't do a ton of. But the point being here is that each of these styles comes with their own set of functions, their own set of sort of useful blocks that make them happen. And so in Snap, it really helps you, or it allows you to support all these different types of styles. So array-based is really dealing with lists as input, treating lists as a type on their own, where we can just apply functions to a list. So hyperblocks in Snap are a manifestation of that, but there's libraries that go way, way deeper. And the final programming paradigm that's on the slide here is this imperative paradigm. An imperative is the type that whenever you look at code online, it's most likely to be some form of imperative programming, because what imperative says is take a sequence of steps, one by one, execute them in order, assign whatever variables you might. Imperative just really says, here's a direction, execute that direction as the program. Loops are a hallmark of imperative programming. So for each item in list, for I equals 1 to 10, whatever it might be, add items to a list. All of those things are examples of imperative programming. So this is typically sort of what you can think of as as an example of an imperative program. So these next few are an example of a block that takes a phrase and turns it into an acronym. So I believe in one of the higher order functions labs, you should have done acronym using map, keep, and combine, which should be on the next slide. But the imperative paradigm here, it really just sort of spells out the steps that we have a script variable, the result of acronym, we set that to nothing. For each item in splitting a phrase, by, in this case, space, we iterate over those phrases, we add the first letter to a variable, report it back. This is do one thing, do another in a loop, report the result. This is a very typical imperative style program. I think this is fairly easy to read in some senses, like this communicates to you, hopefully, what's going on. And one thing here is that it's a hallmark of imperative programming is that we're taking some data like this acronym value and we're repeatedly changing that value. So we're reusing a value, we're updating it as we go along. We're using mutation to sort of keep track of some state and some information that we have. The functional approach to this problem is to use a series of functions where one result gets passed to the other. This is a version of writing acronym that uses map, keep, and combine. And this one is nice in the sense that there's no variables to keep track of. It's just one expression, admittedly kind of a large expression, but the result of each function just passes right in to the other. So in this case, we say keep the items where the length of our list is greater than 3 over a list which is using this block sentence to list. So sentence to list is just a block of the split function actually. Then we map the first letter over that list and we combine things using join. This is in many ways, no variables, right? It's 4 lines of code, it seems simpler, but you do have to recognize that like while reading this code, the thing that we actually execute first is a sentence to list block, then the result of that is passed to keep. The result of keep is passed to map. The result of this map block goes into combine. So there is still quite a bit going on here, and it's not always more obvious what's going on. We also have approaches that are we can kind of say are hybrid approaches. And I think this is a real challenge and also benefit in programming languages. So that the reality that I'd say is most of the code that you look at and most of the tools and projects that you build in CS10 fall into this hybrid approach. So this code is kind of functional, a little bit imperative, and it uses some array style approaches too. So in this case, we explicitly say step one that we're going to keep things in an array after doing the sentence to list. So again, we have a functional thing here, taking a function pass result, but we set a variable. We take the result of that variable and we pass it to our map block where we map item one. And the very last step, we join passing a list directly into the join block. So this is kind of an array-like approach as well, where we have some functional code. We use some state and variables, so it's a little bit imperative. And then we have this array style code at the end. So in practice, you might mix and match all of them. I will say that this is something that in CS10, we do try and push you into this functional model where you're not using as much state as updating or mutating variables, because every time you mutate a variable, especially in a loop, right, that's something where you have to sort of keep track in your head about all the things that are going on. However, this hybrid approach is really a nice middle ground, because what we're doing here is by saying set long words to this keep is I am telling you, the reader of this code, right, that I intend for this expression to represent something which is a set of long words. Now, if we're mean, and occasionally we're mean on exams, we will, name variables, things like foo and bar and garply. I don't know why those are the three words that computer scientists use, but they are, and they've stuck with us. And the variable names don't communicate anything useful, but by separating out step one, step two, step three, where we're never actually mutating the variable long words, right? We're setting it to some value, we're passing that value in to the next expression. We can actually give another person reading this code some information about what we're trying to do by using good variable names. And if there is one thing that you should take away from this lecture, is that being intentional about how you write a piece of code is a super useful thing. That calling this thing long words, calling our map list of letters, right? When I see set list of letters to map, what I should say is, okay, I think I know that the result is going to be a list that looks like A, B, and C, and then you get to double check, does that map actually give me a list of data that looks like A, B, and C? So using good variable names is really a helpful thing. In office hours, a TA might ask you and say, hey, what is that variable? And it's not just what is the name of that variable, but it's, what does that represent? And naming your variables in a way that helps you communicate what they represent can really be helpful. So, yeah, I'm actually kind of curious of just the three styles. So you can put in chat in Zoom or raise your hand. How many people sort of prefer, just as a sense of like looking at this code, looking at acronym, how many people prefer this sort of iterative approach first to something that like you just think it makes the most sense, or you think it's easy to understand, or you just like the look of it and the colors or whatever it might be? Does anyone have a preference of this first style? Cool, we got a couple hands. In Zoom, does anyone have a preference? You can type in chat, raise your virtual hands. Thumbs up, whatever you want. Cool. How many people sort of prefer this purely functional style of like using map, keep, and combine to solve an acronym? Anyone prefer this style? Cool. A couple hands here. In Zoom, anyone on Zoom prefer our functional approach, the upper right over here? A couple hands there. How many people sort of prefer this last block at the bottom? A few more hands. Cool. I feel like I biased the room by saying that is how I also prefer things. Which, there's nothing better than a biased survey to confirm results that you want. That's why we have data science and statistics to figure out how to unbias things. But yeah, I think it is worth just recognizing, right, that as we go through these paradigms, especially these three, because functional, array, imperative, and sort of this hybrid approach, that you'll see all three of them in CS10. You'll see all of them in data 8, in CS61A, in CS61B. If you continue in computer science, you'll see even more styles. So all of these things are worth sort of thinking about. So actually, before we continue on, questions on sort of this idea of paradigms so far, of just some of these examples or what we've been talking about. Yeah, in the middle.
So these all these programs do the same thing. It comes down to like preference and how you
yeah. Yeah, in this case, yeah, that's correct. All of these three examples do the exact same thing. Why you would pick one or the other, in this case, is generally a preference. There are certain tasks that we might say, where one style is optimized for another. So actually, if I have time at the end, I'll demo why some of the array programming stuff works really well in Snap. And that's because we've added a bunch of features to make certain types of computation really fast. And so some programming languages really optimize their environment for a certain style. But in general, all of these are correct. If I asked you to write acronym in Snap, and we're just judging you on correctness, any of these are valid solutions. And you can imagine actually that there's probably, in between these three, right, there's other blocks we could use. There's other forms of even functional variations that would solve this as well. So yeah, all of these do the same thing. It's in this case really about a preference, since no one of them has sort of a clear advantage. Other questions? Any on Zoom? Any other questions? So we'll take a couple examples of sort of imperative versus functional. One thing that's tricky about this is that we can argue that functional programming is sort of a subset of imperative, right? That we're still doing things in a sequence of steps. We can't take, right? We can't pass the result of one function into another until we've done the work to compute that function. Most programming paradigms have a subset of imperative steps. But about functional programming is that we're trying to avoid maintaining state, and that we're trying to think through composing a series of functions in order to solve a problem. So, when we talk about functional programming, it's often that there's sort of one way that is either obvious or semi-obvious of how you might want to do something. So that usually involves something like mapping over listed data or filtering a listed data if we're talking about lists. Some people say this kind of feels like solving puzzles, right? That you're trying to use a set of functions and construct them in the right way. Because you're restraining yourselves to a pure model where every input leads to a function. That output is either the correct result or leads to another function. Trying to essentially write a program where you don't use any additional variables can be sort of a definite restriction. And that's why I think a lot of people prefer things like imperative programming, is that some of these times they feel like a little bit like magic. Functional programming tends to be a little bit shorter. This in and of itself is neither good or bad, but in general, right, we want to sort of maintain some trade-off between, code that is understandable, that's a little bit longer, can be useful because you can understand it, but every line of code that you write is a new chance for a bug. So there is this tension that shorter programs, as long as you can interpret what they're doing, have a little bit of an advantage, but it's not worth making code short just for the sake of making code short. One thing that is really useful about functional programming and why we do push on it in CS10 and in Berkeley in particular is that by avoiding using state, is that your programs can be easier to debug. That when we stick to pure functions, when we could say, this function doesn't rely on anything about this outside world, right? That no matter how many global variables you have in your Snap program, no matter what time of the day or week it is, or the cycle of the moon, that like my function is a pure function, it does the right thing, and it will always return the right result. You think I'm joking about like the time of day or the cycle of the moon, but if you Google for programming bugs that occur on full moons, there is this long history of people running into sort of large systems like Google, like flight tracking databases, where programs that rely on dates and times, they only run into a bug like once a year, or when there's some calendar event that occurs on a full moon. Really trippy stuff that can happen when you write software for millions of people. The last event, the last reason that functional programming can be really useful is that functional programming, by separating out the sequence of steps, tends to lead to better parallelization. So where we can do multiple tasks at once, where we can say, if I take my map block, right, where, let's say I'm mapping letter 1 over a list of data, because that letter 1 is a pure function, I could take letter 1 of one item at the same time I'm computing letter 1 of a third or a fifth or 100th item. And of course, letter 1 is such a quick function that we wouldn't need to parallelize this. But you can imagine that you're actually processing a lot of data, and functional programming can help you run through some of those computations. In a few weeks, we'll actually talk about how we think about running code concurrently on our computers, where multiple tasks can be happening at the same time and some of the challenges that happen there. But functional programming is often a tool that we can use to restrict ourselves such that we can run multiple operations at the same time. Google's web indexing function, right, where it goes out and grabs data about a bunch of web pages, it's all set up in a way using this idea of mapping at a very large scale, that each mapper computes some information about a web page, that Google has millions of computers, every second just computing the same type of data about every web page, generating results in parallel, and then updating its search index. So functional languages or functional programming paradigms have that benefit. Over the last 2 decades or so, functional languages are really growing in popularity. This is not a reason why they're good or bad, but just sort of an interesting trend that we see in programming languages. So that's functional programming. The other one that is really hard to demonstrate on a particular example, like something like acronym, that maps really well from taking a sentence, return some output, is this idea of object-oriented programming. And object-oriented programming is this idea of organizing the types of things that we're thinking about into structures that we call objects, which is a very generic term. And each of these objects has their own set of data, their own set of attributes, and their own set of procedures that they can work with. So in Snap, it's really natural to think of each sprite as an object. So in particular, if you start making games, for which things like the graphics of Snap, the sprites that you might have, costumes and sounds that sprites have, really naturally map to this idea of, I might have a sprite that's a character, and that's one kind of object, and I might have a sprite which is the player's enemy or something like that, and that's another kind of object. And these objects, they might have a name. In Snap, every sprite has a position on the stage, so there's an X and a Y value. And we can do things to those objects. So we can have the object ask a question, we can have it say something, and that say block, right, if I'm on one sprite and I use the say block in my current script, only one sprite will say something at a time. If I have another say block and another sprite, it can say something different. And we can think of those as procedures that apply to each specific kind of objects. So there's really a lot of depth to object-oriented programming. So if you continue on with CS10, CS10, you'll see some more of it. But in Python, we'll see a couple of examples of how Python organizes objects in a little bit more of a traditional way. And what I will show is, if I, not that, let's see, computer. There, where's my cursor now? Oh, cursor is on the other screen. That's why I can't find out what's going on. So in Snap, one way that, aside from just sprites that this shows up is in the sensing tab, there is this block called object. And what this does is it actually reports a sprite as a piece of data that you can manipulate. So myself is a kind of object. The stage is an object in Snap. And you'll note that the stage is an object which has, kind of different properties than a sprite. Like the stage is just this background, so it doesn't have an X and Y coordinate. But every sprite has a whole set of properties that you can access and that you can manipulate. So sprites have neighbors, which are other sprites. I only have one sprite, so this sprite has no neighbors. If I add another sprite over here, I ask for my neighbors, it says no. I think if I do this, it'll say yes. I don't know what the graphical threshold is for what a neighbor is, but basically, a sprite has a function or has a set of properties that are, what are the other sprites that are close to me? And you can inspect that. So we're treating this as an object which has different attributes, and objects have, potentially sort of relationships to one another. I can ask for my name, of course. So the name of the sprite is just sprite. That's not terribly exciting. But the other thing that we can do with objects is one of the nice things about object-oriented programming is defining ways in which objects can communicate with each other. So Snap has this thing called a tell block. And a tell block lets us take a script and have a different sprite run that script. So I'm gonna go ahead and move these two out of the way from each other. So this block, I'll note, is a script in sprite 1, but I can tell sprite 2 to say some message from my code within the first script. So if you look at the 2048 project source code, you'll see that we do this a little bit, setting up the grid, moving tiles around. And this is one of those features of object-oriented programming by saying, this object is responsible for some kind of data. You can better structure and separate your code out to say that the things that I'm doing in this part of my code are responsible just for, let's say, manipulating the graphics of the game board. The things that I'm doing in another part of my program are like the blocks that you built in 2048 are in a more functional style, but they're just responsible for manipulating the lists of the game board. And so Snap has object-oriented programming. There's a lot of different ways that you can explore it. It's not something we typically explicitly teach because it's hard. It's sometimes hard to translate this directly to Python or to Java. But if you want to explore the idea of a sprite as an object, the tools in Snap are there. Actually, before we continue on with other paradigms, any thoughts or questions about object-oriented programming? Cool. So the last type that we're going to talk about is declarative programming. And declarative programming is one of these things which you don't do quite as much of, but is kind of a mind-blowing idea. And the idea here is that we always want to express what we want as a result without expressing how to compute it. So even in a functional programming paradigm, right, we're still telling the computer how we want to compute that result. In a declarative program, we simply describe some rules about the world and the computer figures it out. So this is a kind of interesting example of coloring a map of Germany of each different province in Germany. So the program basically takes in a map where everything's gray, and it sets up to try and color the squares. So we're not going to explain how or why this works, but this uses a language called Prolog. And the really cool thing about a language like Prolog that is purely declarative is that we basically say, okay, here are the four colors that exist. So we have red, green, blue, and yellow. We tell Prolog that what our goal of this program is to have as few colors touching each other. So there shouldn't be a red province next to a yellow province, and there shouldn't be a red province next to another red province. We should try and put red next to yellow or whatever. And so in Prolog, the syntax is a little bit weird. What we're just basically saying is that given this function called neighbor, we don't need to know how or why neighbor works. We say that there are two colors in here, and that the color of one thing should not equal the color of another thing as much as possible. And then what we tell Prolog is, well, how do you know what the neighbors are? So we tell Prolog that there's this thing called Germany, which includes a lot of provinces. And we tell Prolog that in Germany, some provinces are neighbors of each other. So if we look at this map, whoops, right here, right, these two provinces at the bottom, BY and BW, those things are neighbors, right? But BY is not a neighbor of ST, which is sort of in the middle, so we wouldn't tell Prolog that. But we essentially give Prolog these list of rules. At the very end, we ask it for some answers. So we say, color in Germany, these list of provinces. And what we get back is a colorful map where, as far as I can tell, this is a totally correct ordering of the map, where each province is a different color from the one next to it. The program can output an explicit sort of list, right? So we can see that this BY province down here is yellow, even though it looks would be one option, or yeah, I think that's maybe, anyway, there's a couple different orderings of the map, because actually that's green. So, this is an output which isn't shown on the screen, but could be a different ordering. So the nice thing about Prolog as a language is that you just say, here are the rules, here's the environment that I want, and here's, you just go as a program and it tries to figure out all the rules. In practice, working with declarative programming languages requires sometimes a specific set of problems, but it's a useful tool. So in Snap, we don't have super great ways to demo this, but they are an interesting tool to be aware of. So the goal always here is to explore sort of the end result without telling the program how to get the result. So Prolog is one of those languages. SQL is a language for querying data from a database. And SQL is a really declarative programming language, and I'll try and show an example of that as well. Pandas is a data manipulation library that if you take data 8 and data 100 and some other data courses, you'll learn how to use. But it's a similar idea where you describe how you want pandas to make the data look, and then it tries to filter and process all your data to generate the results. So pandas is just a Python library. We won't use it in CS10 because it doesn't really fit in, but that's there. So what I want to leave with the idea here is that all of these paradigms that we're discussing are all equally powerful, in the sense that in any of these languages, if we try hard enough, or any of these styles, if we try hard enough, we can solve a particular question. But some of them are better suited to a task than others, right? We could define some list. We could write some code that tries to, given some constraints, pick a color for the first province in Germany, pick a color for the next province, and build this map in some imperative style. But with Prolog, we basically get to say like, hey, here's what I want, you go figure it out. And that nicely maps to some kinds of problems. But not every problem, is necessarily fit for a programming language. But if we try hard enough, all of them let us solve a problem. Actually, I shouldn't say recall because we haven't talked about Turing completeness yet. But when we talk about Turing completeness later in the semester, we'll come back to this idea that as long as we have a few very simple constructs, any programming language allows us to simulate any other kind of programming language. And so that's really why we talk about programming paradigms. So we only have a couple minutes left. So questions on maybe this idea of object-oriented programming or declarative programming that there might be. Any questions on Zoom? All right, cool. So I will just leave you with one other example of a declarative programming. This is not completing. Okay. This may be annoying actually, since I got logged out. If I can log in really quickly. Yes, that's fine. Log me in. Where is my dashboard? Here we go. So one thing that we're not going to talk about sort of why or how SQL works, but one thing that I think is really useful about declarative languages and SQL in particular is that I can have a number like 171 people signed up for Snap in the last day. And what I can then do is, let's see, where the heck did my, okay, I'm trying to figure out why the edit button moved. So, okay. All right, that's not what I want. All right, I don't know why this tool is no longer showing me the raw SQL. What I wanted to show is just that you can take something like a declarative programming language, just say, count these things, filter this data, and you get results that are really useful. So though we can't show you them in Snap right now, declarative programming languages do have a really cool spot. So sorry that demo didn't work out, but questions, I'm going to start a thread on the weekend. So if you have other midterm questions after the review session, bring them to me Monday. We'll do sort of last second overview. But yeah, midterm next week. Don't stress too much. It'll be, it should be fine. Thanks, everyone. Thanks, everyone on Zoom. See you later.
You too.